symposium, and I hope it will be the first of a long series. So today I'm talking about the network application to neuroscience. So I hope it's enough network neuroscience, together with some friends and colleagues. So the idea of the visibility graphs were defined a while ago as the backbone graphs which captures visibility paths. So let's say locations which are intervisible one to each other in landscapes. So here we have an example of a landscape. Each node represents the locations, and two nodes are connected by a link if they are visible. Also, 1D landscapes can be considered as time series. So if this is time, then is the values. It's not actually like that, but gives the idea of the visibility. This is a more concrete example of a few values of a time series, and the natural visibility, as it was defined by Lucas Lacasa and other colleagues almost 10 years ago, is the following. So you build visibility graphs by taking a few points and see from each point which other ones you can view, let's say. So this is the way the visibility graph is built, so on and so forth. So for each node you have a degree. Then the degree sequence is a weighted network. So for each node you have a weighted degree defined according to the natural visibility, and in this way you build an adjacency matrix which basically maps a time series into a graph. So in this graph, each node is a time point, and the links are, on the other hand, defined by the visibility criteria. After the natural visibility, another criterion was defined, the horizontal visibility, which is analytically more tractable. There are a few very elegant papers by Lucas. And in the practical sense, horizontal visibility is more suitable for short-range correlation, and the natural visibility is more suitable for long-range correlation and non-stationary time series. An important properties of visibility graphs is that they are invariant under several transformations. So stretching, shifting in time, multiplying or dividing by the same values, or trends. So all these time series from A to E give rise to the same visibility graph. Now an interesting extension of this visibility algorithm came a few years ago, a couple of years ago, where again Lucas with colleagues at Queen Mary developed a framework for multivariate time series. So if one time series gives rise to a network, a multivariate time series gives rise to a multiplex network, which is a framework which became very fashionable in the last few years with many applications. So basically, a multiplex network is a network in which the nodes are always the same across layers, but the nature of the connections changes. So for example, you can have a multiplex network in the city where the nodes are places of the city, and the links can be either connection by footpaths or bike path, or metro connections, or so on, or also a network of your friends in real life, or Twitter friends, or Facebook friends. There is an old example of a multiplex network. In this case, with multivariate time series, the nodes are the time points at which the time series are measured, and the links are the visibility for each time series. So this is a cartoon of the framework. So you have 3 time series. For each of them, you define visibility graphs, and then you go and compare the different layers. How do you compare layers? So there are different strategies. The 2 which have been used in the original paper a couple of years ago were edge overlap, so checking how much the edges overlap across networks, or mutual information across layers. Other measures are possible. I will explore a couple of them more later. So, what Lucas and colleagues observed in their paper is that multi-layer visibility graphs are able to distinguish different dynamical regimes in multivariate time series. So they had simple coupled maps which give rise to different regimes. So the turbulence, pattern selection, and synchronization, spatial temporal intermittency, as they call it. And this is varying the level of coupling, different dynamical regimes, and on the y-axis you have the value of the mutual information. I thought it was me. Between multiplex, and you see that indeed this results in clear separation between the regimes, and also, let's say, more precise than other measures. Now, I won't go too much into the details here. Going to a real-life application that they did is the visibility multiplex of multivariate financial time series. So these are stock exchange values from the 98 to 2014. So you have different regimes corresponding to the bubble of the dot-com, the Great Recession starting in 2007, and in the mid-financially stable period. And indeed, they show that this regime is picked up by the multivariate visibility graphs, and not so clearly by mutual information across multivariate time series with different parameters. So, different types of correlated data give rise to network with different structures. You can see also here that for interesting, let's say, organization dynamical regime, you have a more complex network, and you have something which is less interesting in other different regimes. In the same, in the bottom left for the financial time series. So, why visibility and why the application to fMRI? So what drove my curiosity to take this approach and say, well, okay, let's see what happens when applied to neuroscience, is that, well, on one hand is an intuitive idea, which is informative and nicely descriptive. Another thing is that it's robust to processing, is computationally easy, amenable to analytical insight, and is versatile, and it was novel. So we had a master student coming over for a few months, and I decided to get her test this project. Then why to fMRI data? So the motivation for the application of fMRI, in particular natural visibility graphs, to whole time series is that there has been some evidence, starting from work of Enzo Tagliazucchi and Dante Chialvo in 2012, that peaks in the bold time series actually encode information of the dynamics of the whole time series. So basically clustering spatially the regions which have a peak in the bold signal at the same time results in maps which are very similar to the correlation map. And this was further exploited by Liu and Jeff Dine, which proposed the co-activation patterns, showing that basically averaging the time frame of activity of regions which have a bold peak at the same time results in maps which are very similar to the Pearson correlation maps across the whole time series. We also used this this framework a few years ago together with Guorong Wu by speculating that the peaks in bold signal are signature of neural events happening in the cortex and then reflecting in bold signal a few seconds after. And so we use them in our algorithm to retrieve the hemodynamic response function from a resting state data. So the idea is that looking at how peaks in the bold signal see each other is a nice motivation to try a visibility graph in a fMRI. And also visibility allows looking both at local and global activity at the same time. So this is an example of visibility in bold time series, natural visibility and horizontal visibility from a typical bold peak. And here on the left, on the right, you have the adjacency matrices resulting from the two. These, on the other hand, are the visibility graphs resulting from bold signal, where the color is coded by time. So time series recording start here and go on here. So you have 152 time points in this time series. And so you see that these graphs for 3 regions of interest have a modular structure. So what does it mean to have a modular structure in a temporal network? Modular structure in a temporal network speaks to different dynamical regimes, and so to dynamical functional connectivity. So on the left, you have colored the time points belonging to different modules of the visibility graphs as a function of time. And so we thought that dynamical functional connectivity that has been now introduced in the last 4 or 5 years as something necessary to look at, but a bit tricky because as shown by Rickard Indrix in 2016 and Kudela and Martin Lindquist also, the sliding window approach could be problematic, at least for bold signal. On the other hand, other approaches have also been developed by Dimitri van der Ville. So we thought that in the framework of visibility, we could use dynamical functional connectivity as well by looking at partition distance, so the distance between modules, and the Sorensen index. Both measures are nicely coded in the brain connectivity toolbox developed by Olaf and Mika. And so, for example, here we took 2 regions of interest in the default mode network, one in the anterior cortex and one in the posterior cortex. We saw different clusters, and we computed the partition distance based on the mutual information, and we coded the Sorensen index between the 2 modules. So we see this can be a measure of dynamical functional connectivity over time. So as an application, we chose a large open fMRI dataset by Russ Polder and colleagues with 138 healthy subjects, 50 schizophrenics, 50 bipolars, and 45 ADHD subjects. We computed the natural visibility graph for each region of interest, and we computed the pairwise mutual information for each of the intrinsic resting state network defined by Thomas here. So these are the values of the average mutual information across the resting state network for the 4 groups. We saw that indeed for the limbic system we have lower values of mutual information. This is, let's say, already a bit surprising given that the limbic system is a small network in size. You can see it here. It contains a few regions compared to others. But it was actually the limbic system which was different across the 4 groups. So with a statistical test correcting with age of frame-wise displacement, and by looking at the shift function that you see here that quantifies the difference of two distributions across quantiles, we saw that indeed this quantity was different across the four populations. By looking at Neurovault, which is a very nice open science repository where researchers can upload the unthresholded maps of the study, we saw that indeed in the limbic system, together with lower mutual information, in visibility we saw also a lower regional homogeneity and higher coefficient of variation of the Bolt signal, and a lower value of the fractional amplitude of low frequency fluctuations. So this can speak to, let's say, the functional nature of what we observe. Okay, so this paper is published in Network Neuroscience. Thanks to Olaf for setting up a nice home for this type of studies. There have been also some application from EEG to the univariate time series, mainly from the Adeli group, and just last week came out multivariate, so a transfer entropy approach to the horizontal visibility graphs for EEG from the group of K-Stan, which is really nice. On the other hand, they claim that they can solve the volume conductions, and I don't think they can, but still it's a nice application. And as a last application, together with Lucas and Jacopo Iacovacci, one of his students, they applied visibility graphs also to images to found boundaries between levels of grayscale. And so I gave him some images of a brain tumor MRI, and we are trying to see whether the visibility algorithm is able to help us in segmentation, either of gliomas or meningioma patients, and see what this gives. Okay, thanks a lot. If you want to play on the code, here is a GitHub code in MATLAB, and then the original code by Lucas in Fortran, if you're crazy enough to try it. And thanks for your